So I'm delighted today on World Quantum Day to have Peter Zoller as our speaker. And of course, Peter doesn't really need any introduction, but for a lot of the young people in the audience, I'll just point out a few things about his contributions. So first of all, he's one of the pioneers on worrying about things like noise and quantum mechanics. He wrote the book called Quantum Noise with Crispin Gardner. But he's been involved in all kinds of areas of AMO and condensed matter and quantum information. And my experience is whenever we start something new, think about something new, it'll always turn out that Peter had written a paper or two about the subject earlier. So I just wanted to highlight a few things and the things that really have been so seminal in our fields. So first of all, the idea of you can make a quantum computer from an ion trap came about from Dirac and Zoller. So Peter Shor's algorithm was 1994, and a year later, Peter basically launched the field of ion trap quantum computing. He also was one of the authors on using Rydberg gates blockade for neutral atom quantum computing. So we'll give him ion traps and neutral atoms. I guess maybe I can't give you superconducting quantum computing. Quantum simulation with atoms and optical lattices. Again, it started with a theory paper from Peter on the Bose-Hubbard model and optical lattices. And my final example, of which I could have 20 more, is quantum networking, where he was really instrumental in thinking about long-distance quantum networks. And there's a very famous DLCZ protocol, and you can guess that the Z stands for Zoller. So with all those, let's just welcome Peter for whatever he's going to tell us about today.
So let me first of all thank for the hospitality that I'm experiencing here. So I'm here for 3 weeks, and I enjoy very much to talk to all the people around here, and I'm really having a great time. I have to say that I always find it difficult to give a talk at JQI because you are informed about the last things. You are the ones that actually do all of these things, actively. And so I decided today to give a talk which is a little bit different in the sense that I want to talk about projects where hopefully, on the scale of maybe months or so, we will write the paper, finish a paper. So I would like to talk about projects that are at the moment ongoing, and not about, here's this paper on the archive, let me take it and let me tell you what it is, and because you can read it there. So in that sense, I've given sort of the title to some extent over here. You might call it, topics of interest, ongoing work at Innsbruck on quantum simulation, quantum metrology, and of course, I'm somebody who likes very much to do not only theory, but to do in collaboration with experiment. And in Innsbruck, we have, of course, the trapped ion group, Rainer Blatt, Christian Roos, and also Mons, where we have access to these machines and do many of these things together. And of course, I'm also the opportunity together with Thorsten, who is here, to use, for example, the Quera Rydberg quantum simulator for some of these ideas. So one project that we have at the moment, and would like to discuss it sort of with you, and it's not completely finished yet, but it is a theory experimental project. On the theory side, we did a lot of preliminary work. Was this question of bounded error quantum simulation with analog simulators, basically with trapped ions over here, by Hamiltonian and Liouvillian learning. You probably all know what Hamiltonian learning is. It's a quantum system. You would like to learn the Hamiltonian back, maybe also dissipation, like having a Liouvillian over here. But we would like to go one step further, which is that we would like to use these things in order to extract errors and sort of not only give quantum simulation result, but also corresponding error bounds. And we want to do it with analog simulator, even though many of these ideas are also applicable in the context of, for example, digital quantum computing. I'm aware, of course, of the fact that time at the moment is such that everybody, talks about digital machines, with error corrections, all of these things. This is very clear, but I also feel that there's still a lot of life in these analog machines, and this is what we are focusing on here. And then about applications, of these kind of ideas, what we call this inverse quantum simulation, or we always jokingly call it quantum material design, and they give you what the idea is. There's some results around, but they're not vital. Okay. Thorsten Zacher, who is here, will give a talk about lattice gauge theory this week on Wednesday. Wednesday, okay. This was this experiment down here with Quera, just accepted in a prestigious journal. So we are very happy. We heard this news last week. And then this is work on quantum metrology. Alexei was involved when we did this work with Boulder on quantum metrology. In the meantime, we did multi-parameter estimation. We came up with something that we called the quantum compass, where you're trying to do multi-parameter estimation, like measuring magnetic fields in 3 dimensions at the same time. And amazingly enough, you can do these things also with 2 qubits. This is sort of a quantum problem over here. And we wrote theory papers about this more than a year ago. And in the meantime, there's an experiment in Innsbruck, again, with trapped ion by Ben Lanyon. And finally, we have sort of something that's a little bit on the sort of newer, refreshing side is we think about quantum networks, and programmable quantum sensing networks, and about non-local mass superposition. So I want to spend about maybe half the time of my talk about this topic up here, give you some preliminary results, and then talk about the ideas down here. This is trying to run, for example, variational quantum algorithms on the quantum sensing network with the purpose of, doing sort of, this GR quantum interface. So I know many in the people in the audience, you are also working on these kind of things, and without mentioning all of these names explicitly, I mean, I had a lot of fun now talking to you in the last few weeks about some of these topics here. So I gave the title here, Bounded Area Quantum Simulation, but I really talk about more things, and the important point is work in progress over here. So I guess many of you are familiar with this Hamiltonian and Liouvillian learning, where you learn Hamiltonian back of a many-body quantum system for both analog, but you can also do it in a, for example, digital context over here. And I would like to tell you about this bounded area quantum simulation, why we do that, and what the purpose is, and then about this inverse quantum simulation. And I say that, while these experiments are definitely not in the regime of quantum advantage, the ideas underlying it, they work in 2D also, they work also in the regime of many particles. That's the reason why I'm interested. And of course, there was prior work, which was learning the entanglement Hamiltonian, not the system Hamiltonian up here. And maybe I should sort of start out by just reminding you what we learned in this context, because this is what we're sort of taking over now in this new project about this bounded area quantum simulation. Many of these techniques we learned from before. So as I mentioned, the analog simulator in Innsbruck, which is available to us, is trapped ions in 1D. Christian Roos has now about 200 or now even 300 ions. This would be a 2D trap over here. JQI is now 1,000 ions. You can do these quench experiments down here. And of course, all of you probably know that, if you write down Hamiltonians for this setting, this is a transverse field IC model with long-range interaction P field. So when we talk about Hamiltonian learning afterwards, it's learning about what these coefficients are. And maybe terms beyond that, very often when you have trapped ions over here and you miss the line, you get bumps in these couplings, all of that Hamiltonian learning gives that. But we do it at the end really for a different reason, namely for this bounded area quantum simulation that I will explain. So this prior work, where we sort of accumulated knowledge how to do some of these Hamiltonian learning things, had to do with learning the entanglement Hamiltonian in a quantum many-body system. And let me just summarize these things very briefly. We got a many-body system over here, and you look at bipartite entanglement as we have over here. You would like to quantify this bipartite entanglement. And of course, if you look at this region over here, that's a one-dimensional region in the case of these ions that we have down here. This is 51 ions which are here. And you take a subsystem out and you look at the reduced density matrix of this here. Then you can also represent it as e to the entanglement Hamiltonian, which is the Hamiltonian there to be learned. And I tell you briefly about the physics and the techniques that we developed there, because then we carry these things over, even though the setting is really rather different. So what we did in this context is that you say, well, we got a many-body system with a Hamiltonian like the one that we have written over here. Important that it's k-local to be able to learn it efficiently. And therefore also then eventually for a very large number of lattice-sites. Here we were able to do it for 20 lattice-sites. And then you implement in an Eintrap experiment, not natively, but via variational, for example, preparation states, eigenstates, approximate eigenstates, so for example, a Heisenberg model over here. It's kind of interesting because with the Heisenberg model, you know, there's a critical point over here. There's a quantum, there's a conformal field theory, which is valid here. So many of these predictions that we have, for example, for entanglement in relation to entanglement Hamiltonians, they are known for these particular models. And we can try to, on one hand, to develop techniques for seeing these things, but on the other hand, also, you know, we sort of know how to, what kind of techniques we have to develop in order to see that. So what's being done in this experiment is that you prepare ground and also excited state, and approximately it's variational states, and for example, a ground state, and then you heat it up to an excited state. You never do this for a single state. And then the kind of things you might ask is, well, you know, what's the area law entanglement for ground state? You know, this means for a 1D system that it's really constant, or that you have maybe a central charge over here in a conformal field theory. Or for an excited state, you might see thermal entropy over here, like a volume law. So this means linear with L. And of course, we developed techniques for seeing some of these things, you know, in an earlier context with randomized measurement. But here, the goal is now really to learn the reduced density matrix in the sense of entanglement Hamiltonian tomography or entanglement Hamiltonian learning. And so the question was this: well, if I take a reduced density matrix, you know, and I take it out of a certain region over here, for a density matrix, you know, the exponent up here would be an entanglement Hamiltonian, but in the limit that you take a very highly excited state up here, but you would be able to prepare one of these states, sort of appealing to ETH arguments and so on, you would expect that this Hamilton operator that we have here would correspond in the sense that this is like a Gibbs state, a thermal state, would just be the Hamiltonian of the subsystem. If I sort of rewrite that, it would simply be beta, the inverse temperature corresponding to this highly excited state, and then the sum over these local terms and now operate over here, summed over this region that we have here, modulus some corrections on the side and all of that. So this means that the prediction for that is obviously that if I plot it as a temperature profile, and we'll see in a moment why I'm doing that, you know, it's sort of always the same. And of course, you would have a volume law entanglement here. Interesting thing is what happens if you go to the ground state, because conformal field theory makes a prediction that, again, the reduced density operator for ground state, this is this area law thing, you know, has the form of a parabola for this inverse temperature that we have over here. And if you plot these things to prediction, you know, from conformal field theory, applied now to the ground state of a many-body system, should be of this type, and then there should be an area law, including a law correction over here. So our techniques for developing this, you know, sort of led to these experimental results where indeed we could see this parabola here for the ground state. This is plotting this inverse temperature, and for a thermal state, it should be flat. And that's basically what we saw. This is volume and area law over here, and very similar if you go to the gapped phase over here. But the theory in principle from conformal field theory certainly does not apply. It sort of looks similar, it's more triangular and so on. We can talk about these things in more detail. But the underlying point was that I would like to make here, in this context, we learned not only about entanglement, but also underlying was the whole toolbox, you know, how to do this learning over here. This is the corresponding paper I would like to quote over here. Just in brief, you know, we have used in the last few years what we call randomized measurement, where we do, for example, you know, state preparation over here, quench dynamics, could also be this variational, you know, thermal state preparation, all of these kind of things. But what you do is this, that you take a bunch of, for example, data over here, and you design then, in this case over here, an ansatz for this entanglement Hamiltonian, which you then compare, you know, with this data. The essential point being that there's a small number of parameters over here, G tilde, we call them over here. And in our protocol, what we do is this, that we take a randomized measurement for measuring a different local basis. And these probabilities here at the end, we sort of compare to extract the optimal Hamiltonian at the end, and even adding a verification step over here. So this whole toolbox is also used now in the following, where I talk about the problem, which is now very different from this one. It's not Hamiltonian learning, but we want to learn now the real Hamiltonian of the many-body system with a somewhat different purpose. And the purpose is that we would like to do bounded error quantum simulation. And this is motivated by the fact that in an analog setting over here, it's always the question, you know, if you really claim that quantum simulators should be used as a computational device that makes certain predictions, solving a many-body problem, for example, in this under quote quantum advantage regime and so on, the question is, of course, can we trust these simulators? Well, if you can do theoretical simulations for these things, you can compare directly and sort of verify that. But that's maybe not so interesting. We would like to make quantitative predictions in the regime, where we cannot maybe check these things with classical simulation. So the machine is supposed to give you an answer, but also corresponding error bound and explain the error bound to you. And this is what we do. There's a series of papers where we developed some of that on the theory side, but I want to particularly point out these papers by Ignacio where he talks about analog quantum simulators and a regime of quantum advantage and all of that. So let me sort of, on a somewhat formal level, describe what we would like to do, what the basic ideas. It has to do with characterizing, it might also say verifying quantum simulators. I noticed that in particular computer scientists, when you say the word verifying and so on, they have a very different understanding. As an AMO theorist, I'm sort of very hands-on, and we always talk about trusted devices and all of that. There's these famous Mahadev protocols, for example, for untrusted devices. Can you really show that there's a quantum computer behind it and so on? So we are doing these things much more hand-on. There's an experiment, for example. And as a theorist, you might go to an experimentalist and say, well, you got your nice quantum machine. Can you please implement this Hamiltonian? And the experimentalist comes back and say, yes, I got it. Making prediction for certain observables over here, like, for example, a phase diagram, whatever they may be. Maybe somebody also does a digital quantum simulation, even though the focus for us at the moment is really the analog setting over here. And then you can say, can we trust these predictions? And what we do then is that, for example, say with trapped ions, you might do then a quench experiment over here. And you would like to learn back from experimental data, where you prepare different states, like easily prepared product states, and by doing certain measurements, like random measurements over here. You would like to learn the operator structure. This is the operator content of the Hamiltonian back. So you would like to learn, what is the Hamiltonian that you had in the system over here. And the outcome of Hamiltonian learning is that, well, you got a certain, the learned Hamiltonian is a certain mean Hamiltonian. But you also got an error model in the sense, well, you can add additional terms over here and you can find out what they are. But this will be sort of, perturbations to this thing. Your learning tells you that some of these coefficients, sort of, these extra uncertainties that you have over here is like kind of an error model. So there's a deterministic sort of mean part of the Hamiltonian. This is the estimate that you have, plus a certain noise over here. And I would like to call it an error model. Of course, at that point, you can compare if you achieved your goal, that the H over here is really the one H in, but the uncertainty sort of is the one here with these coefficients, maybe stochastic, Gaussian, correlated noise, or whatever these things are. If you do a large number of measurements, this is the error model it sort of extracts from over here. And then comes sort of step number 2 over here, which is now error-bounded quantum simulation. But I said before, if you are a theorist and you can do simulations, you might simply take this Hamiltonian over here, and then from this Hamiltonian, including the noise, this gives you a certain uncertainty, make certain predictions about these observables, and this would be then a bounded error quantum simulation. But of course, you really want this to be sort of self-consistent, that with experimental data alone, in the sense of self-verification, you would like then to make predictions about, the observables over here, including the corresponding error bar that you also want to learn from the machine. And so the idea is the following, that maybe the result that you really would like as a computational device would be that you have an Hamiltonian over here. This is sort of the mean Hamiltonian that hopefully agreed with the one that you had, but at least you know here what it is now. And the exact result really from this Hamiltonian, but the uncertainty comes from these extra terms over here that are these uncertainties that you have here from the Hamiltonian learning, which is sort of giving you this experimental expectation value over here. So you would like to compare, this is what you want, this is what you measure, and this experiment sort of, gives you then the whole distribution based on your uncertainty of knowing this Hamiltonian over here. And the idea is now that, from these fluctuations that you have here, your noise model that you learned in this case, you can derive bounds. Well, there was a paper by Breskill and collaborators now some time ago in one of the conference proceedings. They looked exactly this problem over here, but with a rather different motivation. What they wanted to do is this, that they said, let me take an error model out. How can this is uncorrelated Gaussian noise? Let me try to derive the corresponding bounds. Our attitude is rather that, we are doing Hamiltonian learning and we learn this sort of error model from the experiment, and we are going to use these experimental results down here. And it's really great to see that Breskill et al. worked out, many of the corresponding formulas so we can rely on them and generalize them. Actually, it turns out that the error bounds are very general and not super good. We had to improve some of these things, and we sort of, based with additional knowledge and so on, we were able, and I want to show in the following, get some preliminary results on this idea of this bounded error simulation. So say it again in one sentence. Number one, you measure here Hamiltonian learning, and you learn sort of an error model over here with some uncertainty for these additional operators. And this gives you then sort of bounds over here to what extent you can trust the quantum simulator and the experiment, giving you an expectation value that really corresponds to the Hamiltonian that you wanted, even though the experiment realized the things with a certain uncertainty over here that you had from Hamiltonian learning.
Now, are you assuming that the experiment is going to learn about the errors by repeating the experiment and seeing
Yes,
how
you will see that now. I talk about the details of that, okay?
Now, in the Pascal model, presumably the underlying assumption is that whatever these errors are, that they have an average of 0.
I mean, okay.
Can't guarantee that.
Can I show you afterwards what we actually do? So I'll come back exactly to that, okay? So in this sense, you have your Hamiltonians over here that are distributed by this uncertainty. This is what the experiment gave you back because you were able to do a finite number of runs. And there may also be a sort of more fundamental, like systematic errors that you didn't learn all of the terms here properly. So this is sort of the deviation from the, theoretical, from the expected result. This is what you would like to do. Remarks over here, the reason why this Hamiltonian learning works is, of course, I mean, this is well known that these are k-local sparse Hamiltonians, so only we have a polynomial number of parameters. This is to do with this learning in the limit of quantum advantage. And let me also add that we not only want to learn the Hamiltonian, but also the Liouvillian. You have to assume a certain model, like, for example, that you believe that your noise is like in a master equation. Doesn't always have to be true. So kind of a quantum white noise or classical white noise. And so you want to learn the Hamiltonian and Liouvillian at the same time. So learning the noise model at the same time that it could be classical quantum that you learn this Hamiltonian. If you do quench dynamics, that's very important. So what we do in the following is that we learn Hamiltonian, which is a dominant part, and then the noise model, which is sort of much more difficult because, it's down in the noise basically that we have over here. I have a few slides that I just want to tell you. We can talk about this, basically take these ideas of Preskill mathematically, but we reformulate them now for the Hamiltonian learning. They will go these things, this is what we want to simulate, and this is, so can we put bounds over here, for these observables with a wrong Hamiltonian, taking from the whole ensemble over here. And then deriving, bounding the expected error, bounding the distance from the mean trajectory and all of that. So there were all of these formulas derived. I will show you afterwards simply things like that, but now embedded in an experimental result, at least to what extent we have here now at the moment. So if you're interested in that, we can talk about it afterwards. So I'm ready to speak about that, but I don't want to do that. So how do we do now Hamiltonian learning? Well, I should say that there's an infinite literature on these things. Theoretical, and I apologize if your papers is not listed over here. Here's some papers that we wrote in Innsbruck. There's very few experiments. It's sort of amazing to see single qubit. Google only did 5 qubits. I think they had problems with drifts and so on. And the principal Sycamore processor had many more qubits. Looming Duan did an amazing experiment with 300 trapped ions, but it was sort of limited to a very simple Hamiltonian. Everything is commuting over here, and then they learned the JIJ, but 300 ions is very impressive, I have to say. But the whole setting was, sort of, I would say, at an early stage of asking complicated questions. We really want to look at this like a black box learning. You have an experiment, and you go there and want to say, I want to learn the Hamiltonian. I have some prior knowledge because I implemented a certain Hamiltonian that I wanted to do. But then you're really learning not only the parameters in this Hamiltonian, but maybe additional corrections or maybe bumps in your variables, whatever you have, that were not on your radar screen. So really want to do black box learning to characterize your quantum process. And the assumption is this, that, well, let's assume that this is the master equation over here. And you can see that we have 2 terms. On one hand, the unknown Hamiltonian. On the other hand here, I wrote down Lindblad terms with jump operators of some weak dissipation. We expect this to be much less than this over here. This is a good quality simulator. And what you do in this business is that you make for this unknown Hamiltonian is in certain ansatz, in terms of an operator basis, like Pauli basis, that you make higher and higher, at the same time introducing more parameters, which then introduces more noise. And the art is, of course, to make iterative improvements for the whole thing, where you learn the dominant terms, the smaller ones, and so on. So this is really machine learning to some extent, and you want to do the same thing also for this Lindblad dissipation down here. Put in collective dephasing, maybe local dephasing, spontaneous emission, all of that. But you really want to learn the operator structure of that over here. And you can see that the unknown coefficients, are these C's and the D that we have over here. And the approach that we took, and there's many out there in the market, and in this particular experiment, actually 2 different techniques were taken, but they can also be explained over here, is this: that we simply said, well, when we have write-down Ehrenfest for a certain observable, observables could be just single qubit observables over here, 2 qubits, you can do randomized measurements over here, pick a set of observables, and you prepare them in a certain initial quantum state. At the end, you pick many initial states, and you want to look at the time evolution in your quench dynamics from 0 up to the time t. You can see on the right-hand side, we have now here this observable that we know because we measured over here, the unknown Hamiltonian, and then you also have here these Lindblad dissipation terms. And you want to learn the Hamiltonian in the sense of these operator ansatz, and also this Liouvillian in terms of learning these unknown coefficients. You can see that what experiment provides over here is the left-hand side, that for different times t, this is a different length, how long you run the circuit over here. You can, the initial condition, you prepared product states, for example, and then you measure at a certain time t, and then you get a long list of constraints, and then you're asking, what is the best Hamiltonian and also dissipation compatible with this data that we talk about over here. So there's some post-processing over here. You have to do some of these integrals, but you have to estimate. So a long way. I think that the maybe most interesting plot in this context is this, that that one does this, what I would call now here ansatz assessment, that you make an ansatz over here that you want to expand, bigger and bigger, bigger, more and more terms, exploring what additional terms there are. And you want to plot this error, this is the error over here, versus the number of experimental runs. So experimentalists, when the number of runs in these ions exceeds 1 million, they get very unhappy. And so it means that you would like to do this learning, with a limited number of experiments. And of course, how well you can learn out of that depends on how many parameters that you choose over here. So there's always this compromise, that how to extract the data. But in the experiment, data are taken, and you can do the different kind of processing afterwards. But you can see that basically this error, and we can extract this from the experiment, always has this feature that, it goes down in the early stage, like, for example, being shot noise limited down here, and then it develops a plateau. The shot noise over here simply means, well, you got shot noise in the experiment, and by improving the number of measurements, doing more and more, this is reducing this thing. This is, for example, this Gaussian error model that I mentioned before. But then you see a plateau, and the reason for the plateau can be a very simple one, that maybe your ansatz over here was insufficient, and so having a good ansatz and an even better ansatz that you can do by this post-processing, you can sort of try to fit, what is the so a better ansatz is the one that gives you a lower plateau down here. And of course, you always hope that this knee, where you go from shot noise limited, from the shot noise dependent to this plateau, happens at a very early stage. Okay, so the art of post-processing is to sort of optimize these kind of plots over here. And but the statement is shot noise over here, and then plateau tells you about systematic missing terms in the answers that we have up here.
Maybe an atomic clock person, so that they're going to say, oh, that means that the noise is not white. So which often
okay, that's right. So I said before, at the moment I explained this thing for the model, where we say we have a master equation and we assume it's true. Very often in the experiment, it's not the case. I mean, one example is if you have magnetic field fluctuations, very often that during one run, they sort of vary between different runs. So they are sort of a kind of a static noise, if you want. We can extend these models to include this. And another one would be, of course, that there will be drifts in the experiment, from one experiment to the other one, very slow drifts. And then, of course, what you learn, and you would see that in these kind of plateaus over here, that this would level out is something that has to do with this drift in the experiment, because you have to do this maybe 10 to the 5 or 1 million runs in order to find that. Yeah? And so you're completely right. I'm explaining the most simple version over here. In the experiment, it was the laser noise that was dominant. And the laser noise can be described by a master equation here. And so the magnetic field dephasing, what I thought for a long time would be the dominant error, is not the one, and then the model would be wrong. So I think that's exactly. But let me make a second comment about your atomic clocks. So when you do parameter estimation, and you measure phase in quantum parameter estimation like you do in an atomic clock, maybe the proper way of doing that is you got all of these collisional shifts that are in there. To do a Hamiltonian learning, but the Hamiltonian would be the one of the unperturbed two-level atoms, and you got all of these other terms, assuming that they could be described by a master equation that you could learn. So a proper way would be also in an atomic clock to learn it as a many-body system, extracting the parameter that you really care about, and then it would be these nuisance parameters that are these other master equation terms. But we are not there yet. So, okay. Okay, so I just want to say that, well, and then you can leave learning and should be impressed that we have 10, but also then 51 ions. I'm not going to explain now the details of these, couplings, going down polynomial and all of that about its error bar. I think that the interesting part is that when we go over and we want to do now things by taking the learned Hamiltonian and taking, for example, this kind of a noise model here, put it into theory and plot for other observables that did not enter the picture here. For example, experiment, you take an observable and you develop long time. Hamiltonian learning was done by about 0 up to the 0.2 or 3 over here. This was the interval where we learned the Hamiltonian. Then we took another, observable that did not make it in the list where we learned the Hamiltonian down here, different ones. And then we can predict, what is the corresponding error by simulating now, in this case, classically, this noisy model up here and compare with the experiment. And you can see that, this is where the Hamiltonian learning stops. And this is sort of the prediction that is not too bad. This was an early result. So, it kind of agrees quite well. So usually we are pretty well within this error bar that is predicted, from this learned Hamiltonian for these other observables that we have over here. I told you before that, when you do this error assessment, and I will not explain now what the error was here. This was the ratio of two singular values that sort of measure how accurate the whole thing is. You can see as a function of the number of runs over here that we always see after some time, what is supposedly shot noise limited. So go down here, but we see some deviation over here. We are not entirely sure what this thing is, and this is maybe exactly what you said before. These are probably drifts, that we discover over here. And you can see here a slight onset of plateaus and so on. But we would like to see a much sharper knee in this thing happen. And this is probably just what you mentioned before, the underlying reason for these things.
Never trust just one point. Should indicate that there's a plateau.
I agree, but for some reason, experimentalists don't go over 10 to the 6 over here. I'm not sure why, Maybe it has to do with the lifetime of graduate students. So okay, good. Yeah. And then, of course, you can go and do the same thing. This is sort of the most recent plot for these predictions. And you can see that there's, for quite a long time, for pretty funny and strange observables that we dig over here. This is now really a theoretical simulation. This is the same thing with experimental data and the learned Hamiltonian, where we apply this Preskill time error bounds to the whole story. And here we include dissipation. So I'm not going to discuss now in detail, all of the results. These are the error bounds down here. We can see that they get worse and worse because they're sort of, short time error bounds, what we have in this thing over here. But, this is the Preskill error bound. This is sort of then our corresponding, result that we have over here on the measured. Then we take these experimental data and then we analyze all of that. So this is this bounded error, quantum simulation over here. And you can see for a long time it gets kind of meaningless over here. But for short times, I would say that this error bound is pretty well fulfilled. So this is what we are doing at the moment. We are not final with these things over here, but hopefully could get across what the ideas, what the message is, what we want to do. We want to learn, black box Hamiltonians. and use them sort of as an error model then, to bound only within experiment corresponding observables. That's kind of our goal over here. And we are, I think, sort of getting slowly where we want to be. Let me just add one addition, okay.
Want to get into the long times, right? How do we get there?
For long times over here, what do?
Yeah, I guess for advantage, you're saying like what care about?
Okay, you talk about quantum. So this is not a quantum advantage experiment. We only say that the techniques, would be applicable in this regime. I think it would be first of all much more interesting to go to, for example, 2 dimensions. Long times, of course, when it's dominated, and also by dissipation, these things damping out. So this is becoming more important. So yes, you want to go to long times, but of course also large systems in this case.
What do they need to change to be able to get the balance that they're good for? Let's take more shots.
Okay, so I have to tell you a little secret. When these experimentalists did these experiments, they took an enormous bunch of data, and then they dismantled the experiment because they upgrade from 50 to 100 ions. And of course, we then came back and said, we need one more data set over here. This is missing, okay? I said, okay, wait 1 year until the apparatus is back online, then with 100 ions and so on. So, okay, don't tell anybody else, okay?
Time and units of the coupling.
Okay, so the coupling is always this 720 per second. You can convert that to hertz, and this is now milliseconds over here. So the scale over which we learn typically, is sort of over here, this Hamiltonian, and then the rest is sort of predictions that we make out here. And this is a few 1/j, the dominant couplings, the whole thing, okay, what you sort of expect, If you go to longer time, this thing settles down, and it turns out that this integral estimation that I talked about there becoming very noisy, and you need intermediate data. So there's some, okay. But I think you got the point of why we want to do what, and that this Hamiltonian learning is not only while you learn the Hamiltonian and you enjoy it and you go home, but it maybe have some deeper purpose in doing that. And we can do the same thing also by having digital circuits and then sort of learning Hamiltonian back. That would be the effective time revolution generated by your, including trotter errors and all of that. And we have done theory along these lines. So let me move on and just make a slight comment on something that we call inverse quantum simulation, quantum material design, a problem that Christian and I started, and actually Pasha from Harvard, one of the Misha Lukin Dembler students, joined this project, and there's some results. I just want to give you the idea over here, because I think it is very cute that it's also putting some light on these additional ideas. So what we want to do is this, that normal quantum simulation experiments work like this. You take a Hamiltonian, go to your experiment like Fermi-Hubbard, and you get a phase diagram out. For example, I'm always making this joke, maybe searching for D-wave that we promised with our quantum simulators with fermion for a very long time, and you would like to observe that. Then you do the experiment, maybe you see nothing over there. At that point you say, well, maybe I don't trust my theorist that told me that, because it turned out that he was an addict of mean field theory, so getting wrong results. Whatever the reason could be, normally theorists are right, of course, I have to say. But then you do Hamiltonian learning, and to check, first of all, is this Hamiltonian really the one that he had over here? Hamiltonian learning is at that point useful, and of course this thing passes the test. It's an 2D Hubbard model. But then, this Hamiltonian in this sense is this verification step that I talked about, and you can prepare ground states, approximate ground state, or thermal states, and learn this Hamiltonian. But the idea of this inverse quantum simulation is sort of to turn things around. And we would say, suppose that you draw a phase diagram by hand. Okay, big D wave, for example, would be a desired feature. And then you're running a quantum simulator, fermionic quantum simulator with Hubbard models, for example, or whatever your favorite is. But you could also do that with classical computations, but they may be too hard, like for the D wave case. And what you would like to do there is I take as a cost function the feature that you want to amplify, like D-wave, and you put it in a cost function. I want large D-wave over here, D-wave order parameter. But at the same time, you would like to get a state out over here that would be very close to the ground state of an Hamiltonian. So optimizing low energy and a large D-wave feature over here. And then you do Hamiltonian learning back, what is the Hamiltonian that gives rise to the phase diagram that I desired, or the features that I wrote over here. This could also be susceptibilities, whatever these things are. And I just want to show you as a result, if you do that in this case, for the simple case of a 1D ladder with fermion optimizing for D wave, what Christian and also Pasha found is when you do that, they learn something that the flat iron people taught us a long time ago. Turn on cross coupling and you get D wave. If without that, there's no D wave, and with these things, a D wave. So it tells you, here have a D wave becomes larger if you add cross couplings on your plaquettes. And I think that this whole procedure is actually, asking this question this way to learn the Hamiltonian back from the system, but here in a way of using a quantum simulator in between that optimizes a cost function that amplifies certain features, certain properties that you want from your quantum material. That this is a very general question, and we have some first plots of optimizing for high TC, for example, not only Hamiltonian and so on. You can see that Hamiltonian learning is rather sort of useful framework in this case by doing inverse quantum simulation. Okay, I have to hurry up now. Second part, quantum metrology. I want to tell you just what the basic ideas are, what to do. So I've for a long time been interested in quantum metrology, interface to quantum information, and I want to tell you about work. Charles is a student of Hannes Bichler, who is allowed to work with me, and Thorsten is here, and Denise is also involved in this thing. And I've just called it here, emulating atomic clock interferometers with quantum networks. Steve was kind enough to mention before that we have a long time interest in quantum networks. We want to use them now as quantum sensors for non-local, but at the end, of course, to hope to discover maybe some new and interesting physics, and this GR, quantum interface that also Jake Taylor does here, for example, is somehow quite interesting. So the idea is sort of this, that all of you know atomic clock interferometers. You have two-level systems like your optical clock, but you can also make spatial superpositions. And the way to look at it in the context of this gravity is, of course, that you would like to probe non-local mass superpositions. According to relativity, mass and energy is really the same. And of course, this atom being ground to the excited state has slightly different masses. And you would like to do that. The goal of atom interferometers is always to get a very large separation of the beams. And the idea is now to map this thing onto quantum networks where you only have entanglement of internal states. And we've been working on this for quite a while, and we were we saw that there was a paper with similar ideas now on the archive. We are doing slightly different things. So let me tell you our story, but I want to acknowledge this work over here, which at the end has quite some overlap with what I will tell you now here by Beauregard, who is, I think, now in Cambridge again after being in Denmark. So why am I interested? So you can see here we have developed tools for quantum communications if you want to use them now in the context of quantum sensing. In contrast to these atom interferometers, they will always be limited. You can go to very, very large distances, just keyword quantum repeaters. This is interesting, in particular, as one example for the gravity quantum interface, but the applications are many. And what we would like to do is, at the end, we want to run some variational quantum sensing algorithms on these quantum networks here, in the sense of a non-local Ram's interferometer, and I will explain to you the basic ideas now briefly in the following. Junier invited me to write with him this essay here that came out last year, what the future is in quantum metrology. And the answer was, you might guess, quantum information, the interface with quantum information. And so we talked about all of these systems over here. And of course, June is the master of quantum metrology. And so he sees the future, in this interface. We are doing quantum information. We learn how to create entanglement in the lab, local, but now in the case over here, non-local, and how do we benefit now in developing sensors for this thing here. Historical remarks, we did a few years ago. Yeah.
What was John and Norman's picture for?
Well, these are famous people involved in this case over here. Maybe when I put them over here, they write good letters for me. Okay. Well, Rams is clear. Rams interferometer. Yeah. That's right. It's a slide I prepared at one point for Harvard. So of course, John Doyle with his whole, and June, of course, deserves to be anyway. That's right. Yeah. Okay. And there, what we did was this, that we said, Rams interferometry, all of you know, why don't we put variational circuits over here at the very beginning and at the end here for the measurement and here for the input state that optimize certain features, like you define a metrological cost function where on the wish list you have signal to noise ratio, but you might add more features like, a broad dynamic range and all of that. And then you have the available quantum resources and you optimize all of that, with the classical computer, finding the best pair of entangled input and entangled measurements that you can do. And the results were the experiment over here that was published now, I think 2 years ago, something like that. This is normal interferometer interference fringe. This is a noise down here. And, this is sort of the shot noise product states over here. And you can see that by making a squeeze, actually spin squeezing here, the noise goes down. And if you add a decoder over here and be asking, please find an input and measurement state where this noise is as low as possible, but also as broad as possible here for a dynamic range. Okay, a GHZ state would only have Heisenberg at one point if we wanted to have it broad. And now you can see that if you add at the beginning of circus, at the end of the circus, you go low, the red curve, and very broad. This is what we ask for. So this is running variational circuits, on a, in this case, trapped ion quantum computer that acts now as the ramp interferometer to measure this thing. But now we want to do these things non-locally in a quantum network, and I will tell you now briefly, what the idea is behind it, what we want to do. So I'm involved together. Alexei was also part of that, with June and Anna Maria in this QSense project. And of course, all of you know that June did this great experiment where he was able to measure the gravitational redshift, over 1 millimeter. Kolkowitz, I think, had 1 centimeter. So these are amazing experiments. But what they're doing is that they go basically to the limit of, measuring gravity smaller and smaller. And this is amazing that you can do it experimentally. But I would say the actual thing that we should try to do is not go smaller and smaller. I mean, this is a demonstration of these optical clocks, which is just amazing. But actually go to large distances. And how do we do that? And maybe also multi-node sensing here. In Innsbruck, there's trapped ion experiments by, for example, Ben Lanyon over here. We have a 230-meter quantum link, and they could also try to do sort of measure gravity now on these quantum networks that we have over here. So you would like to benefit now from the development of quantum communication, being able to measure, to create entangled pairs over distance with quantum repeater protocols, whatever they may be, and benefit and sort of come to a new atom interferometer. We really would like to emulate an atom interferometer or an atomic clock interferometer on a quantum network, non-locally, but using internal degrees of freedom and not sort of splitting the center of mass. So this is the question that we were asking. The standard atomic clock interferometer is a 2-level atom, and you bring it into spatial superposition above Earth. So there's this Newtonian gravity term over here, but there's also this very small redshift over here, which is really tiny. This fact over here, independent of mass, is 10 to the minus 18 for 1 centimeter. As I said, June was able to measure that really for 1 millimeter, which is amazing. And we want to emulate this thing now only using internal qubits on a quantum network over here, and using the programmability at the end of this quantum network. So to probe sort of, in this sense, non-local mass superpositions, this has a foundational aspect. We really want to have entangled states over a large distance, but feeling now gravity. And on the other hand, then, of course, what we do right away to mention this is that we are trading here big terms like this Newtonian gravity to this tiny, tiny redshift over here. And so at this point, you're only measuring redshift. So the signal is much smaller, but you have the advantage of going much, much further to much larger distances. This is sort of how we see that. But that's, I guess, sort of coming as part of our quantum revolution. I have here some slides that I think I will just basically skip. Equivalence principle, if I got an atom, 2 internal states, they have different masses. And the excited state and the ground state. So this is a bigger mass than the one that we have down here. But the difference between these masses, this is a problem over here. It's just, the optical transition frequency times h bar divided by c squared. And this mass is really, really small. And so at the end, we're going to ask, how can we magnify, even though this mass, we always call it a photon mass, and a quote, it's not a photon mass, but just the energy of the photon that corresponds to that. You can see that the redshift is basically this very, very tiny mass times g times the h, which is a distance over here. Want to mention that there's all of this theory that tells us how to write down these equations. As a theorist, then you don't have any sleepless nights anymore, because you know that professional people in GR derived all of that, including all of these correction terms. A little bit disappointingly, maybe, only the redshift sort of survives in our context here. Would like to see more, but that's not the case. But we want to make the redshift large. So first of all, let me tell you that we can turn it off, of course. If I go to an excited optical clock state, we can turn the redshift off by just, taking this quantum state, putting it down in one of the low-lying states. The redshift here is basically 0, so redshifts can be turned on and off. That's very convenient for the following. But of course, also the redshift gets larger. When you put entanglement, like here atomic ensembles, you get basically potentially factors of n. So you want to do these experiments with many atoms, entangled as you will see now the following, and in this sense, engineering non-local mass superpositions. But let me also point out that I find it very exciting that, these, for example, nuclear clocks, scandium has 1.4 kilo electron volt, nuclear excitations. There, the redshift becomes really, really large, and if you do the same thing in a solid, having many of them, there's really the potential that nuclear, clock transitions may be the right way of implementing all of these ideas. And obviously, our belly is just getting numbers better and better, but there may be a fundamental reason. So we would like to construct these networks with optical clocks.
Is there any hope of making an atomic pocket?
I trust June.
Yeah, but, well, I mean, he's done a great job on the thorium, but that was only 8 eV. We're talking, 1 keV.
Well, there was a Nature paper that talks about 1.4 keV, and I'm saying that, maybe now they have a reason really to develop that, Okay, so, no, I mean, that's right. Okay, so I'm only saying there's a potential, to do these things, and if there's a reason to do that, this may be one of them, that you want to get these gravity terms really much larger than what we have at the moment. So let me now talk briefly about, what is a problem and what is sort of our goal. I mentioned before, we want to run variational quantum algorithms on this network to improve all of that. Let me now tell you what the ideas are. This whole thing has these sort of foundational, let's test, in the presence of gravity with GR effect quantum superpositions. I guess there will be no surprise. Like in Bell inequalities, there was also not a surprise, but seeing them was fundamental and maybe similar over here. But also at the end, this may be a tool to measure GR and probe it on space-time on a very global scale over here. So I find that interesting. So what is our problem? Okay, our problem is this, that, okay, so we made an EPR state, on a quantum network, an excitation sitting on the left-hand side and one on the right. If you run a quantum repeater protocol and you get your photons, there's really two ensembles. And then you get a state like, well, here all atoms in a ground state, here's one in another state, and then here's one in another state. So this is a non-local, this is an EPR state. But I told you before that the mass of that, there's obviously a mass superposition, but this is really, really tiny, just one excitation, MEG, but this is the one that quantum repeater protocols give to you. So how do we grow this state, So what we want is that we can grow these non-local cat states, if you want, to something that has maybe many more excitations, therefore increasing the effective mass of the whole thing. The bigger, the better, maybe taking large ensembles, keeping coherence with all of that, or then maybe even making states like, well, you have here a mass M0, but you want a superposition of two masses on the other side. With these atomic systems, we can engineer all of that, but the question is how to do that. And this is where variational algorithms come into play. And we have learned sort of, from our previous discussion how we might be able to do that. And of course, the setting that we have in mind is neutral atoms cloud, maybe in cavities, or maybe also trapped ions, could be quantum computer. And let's adopt now a language. If I have a cloud over here, and I don't only have global addressing, I can think about the symmetric state. All atoms are in the ground state. One is in the excited state, but I don't know which one it is. So symmetrized state. And there's this whole angular momentum ladder over here that we very often represent as a Bloch sphere that we have here on the right-hand side. Now we can ask, can we grow this state that I mentioned here before using just local global rotations and maybe one axis twisting? And let me show you that this can be done by running variational quantum circuits on this quantum sensing network over here with the goal to optimize the cost function. The cost function is here, large mass superposition states. Global addressing is, okay. Squeezing is sort of known, there's all of these papers out. So we are building on resources that are available right now. So we want to develop a toolbox, shallow depth variation circuits running on the quantum network over here, where this state over here with just one excitation is now grown, and we put here many excitations, to increase the mass difference from m0. This is all atoms in the ground state, to some of them being in the excited state, but of course keeping the coherence, of this whole entanglement that we have over here. And we want to do that, of course, with local operations. Getting this state over here, the entanglement was very expensive, with your purification, quantum repeater protocols. You just, made this thing. So we applied local operations to grow this excitation to the one over here. And maybe then also the other state that I mentioned before, having sort of more heavily engineered mass superpositions, which we have here. So in that sense, when I have here a seed state, which is this entangled state with just one excitation that quantum repeaters give you with the superposition down here, we would like to move now this red dot sort of up here systematically the ladder, increasing the masses. And this is a Bloch sphere visualization of this state. I'm drawing here the Bloch sphere. Actually, Charles did this thing, drawing the Bloch sphere. And I'm plotting here the mass. All atoms are in the ground state. And here, one atom, you can see there's a slight offset over here. This thing is really tiny. These masses are very tiny in the seed state that we have here. This is excitation. So we would like to move this bar up here, this whole ladder, to make our large mass excitation. If you want to see what this state is, look at it from the bottom, then you can see that this is all atoms in the ground state. And this is sort of one atom excited, but you got many others around. This is a slight ring around it. So we got here this ground state, and then we got the ring. This is this excitation. So we got the non-local Schrödinger cat. This thing is in the ground state, and this is in the ring over here. And this is in the ground state, and this is the ring over here, which is this mass excitation that we would like to engineer in this context. So can we now move up and even split this ring? Well, to give you an example, so what we really want is that we get mass states that have many excitations, like a mass M1 and an M2 over here. And here's what we get variationally by a very shallow circuit. You can see on the Bloch sphere, this quantum state looks pretty crappy and not really what we want over here. But the mass superposition that we're able to engineer here, they are pretty good. I mean, maybe some of the phases between these states are random, but this is really what we care about. So we can make we can grow mass superpositions non-locally, and split up this thing by sort of developing quantum circuits. And what they have to do is this, that they do not touch this thing down here. You got sort of the superposition state. So one is in the ground state, and then the other one in the ring, and you move up the ring without touching, your ground state, which is in the superposition here, the ground state, one over here. Can we move up this ring? This is like doing a gate on this Bloch sphere if you want, and if you do that variation with a very shallow depth circuit, 3 layers, this is what Charles has done here, this is what you get. And maybe I don't explain now how this works because I'm sort of going over time. And the new physics that we want to see is, of course, probing these non-local mass energy superpositions, now implemented on these quantum networks using this tool of these variational algorithms running on a network. So if I go back to this atom clock interferometer, if you write this thing down, you can see that you got the spatial superposition, you got an internal state superposition, and the feature that you have over here from the redshift is that you got Newtonian gravity, but you got here also the redshift showing up. So there's sort of 2 frequencies, and there's been discussions by, for example, Jaslav Bruckner as a gravitational decoherence or then dephasing, that when you make these superpositions, you want to see these decays, but after some time, a revival as an indicator that your quantum superposition sort of survived. This is this interplay between the Newtonian gravity and the redshift. One is to say that these experiments, this was proposed, but it was never done. In papers like the one over here, where the experiments, they don't exist, they're just too hard. Maybe with what we talk about over here, this could be done. So we want to emulate this situation here, like, for example, on this network that we have over here. For example, creating these 2 mass superpositions that would mimic this situation over here. So if you want to emulate that on a large-scale quantum network, you have to create these states that I was talking about now earlier, with these local mass superpositions, mass M1 and M2, relative to the reference mass, which is all atoms that we have down here in the ground state. And if you do that for the ideal case, but also then for the variational, you can see if you just have 2 masses, you see atomic interferometry interference fringes. This is sort of over a distance. You can see that we have a little bit more than 1 mass over here with our variational circuit. it's looking not too dissimilar, but of course this is not ideal here because it has the same frequency, but the visibility is reduced. When you have now two masses over here and you do this variation state, you can see this is the ideal situation. This is what Bruckner studied in the case of the atomic clock interferometer. But over here, we can, this is what we get for the variational. So we don't want perfect agreement, but we want the basic features that we can see over here of these mass superpositions to be visible in these sort of non-local interference ranges. So what we're doing here is really that we are running here a non-local Ramsey protocol. You know, they have entanglement, you distribute it, and then you have a huge interferometer, you know, that senses this redshift, and then you would like then to interfere these things back. And I should talk about the measurement over here, how we do that, but I guess I don't have time to do that right now. And it's sort of interesting if you do a coherent state, which is now a superposition of many different masses. You can see this dephasing and this collapse over here. This is what Bruckner called, you know, gravitational decoherence. I guess it's the wrong way. It should be gravitational dephasing, but also the corresponding revivals. And this is our sort of variational way where we have this, you know, one excitation that we grow then to a coherent state on one side, and then we can see that, you know, that this leads to that. So I sort of put now here together, you know, a bunch of ideas, and let me just show what I had, you know, as my beginning slide. We have this bounded area quantum simulation where we're sort of on the way of being able to measure in experiments, you know, bound for observables. This was the ultimate promise, you know, of quantum simulation. But then also, you know, down here, this non-local mass superposition where we are running variational quantum protocols here with the purpose to grow, you know, big mass superpositions that non-locally that are built on using quantum communication networks, and then making certain mass superpositions non-locally based on sort of existing technology, I would always call it. I mean, there's a long way still to go here, but I think that the basic ideas are very clear. So it's really quantum networks were developed for quantum communication. Let's now use them for quantum sensing, okay? And with quantum repeaters and all of that. And let's now optimize cost function there that want to see certain features in quantum sensing that we care about, in particular this interface of GR and quantum, and maybe at the end measure something like the metric or whatever on the very non-local scale with multi, you know, node settings and so on. That's of course a long-term vision, and but I'm sure our experimental friends will take us there at one point. Thank you.
We're running a little late, maybe a couple of questions.
In the Hamiltonian learning part, sensitive is are the observables that you choose in the experiment to the Hamiltonian structure that you're doing. And because experimentalists really don't like to spend much time in the lab, can you feedback as you learn to change the observables to better match what the Hamiltonian?
Yeah, okay. So usually the strategy is this, that you sort of identify certain observables, maybe just, you know, one particle observables like spin measurements, different directions, and or maybe also on your random basis, and so on. What we eventually do is this, that we're using randomized measurement in the sense of shadows over here, you know, that give you multi-particle correlations. And if you do experiments, you know, it allows you to extract via classical shadows a correlation function that you can sort of choose afterwards. So it is during the analysis that you find, you know, that, maybe this is more sensitive than the other one, but you've taken experimental data without taking additional ones. You know, classical shadows, I think, are sort of the ideal interface for these kind of things over here. At least that's what we found. Yeah.
Okay, one more question.
You have thoughts for expanding the learning of to other kinds of errors that you were talking about?
Expanding to other kind of errors, what do you mean?
Like you were saying that it was just a Lindblad model that you're doing right now.
Oh, okay, yeah. Okay, so there's two limits, you know, quantum noise or noise in general. There's two limits. One is the white noise limit. This would be captured by the master equation by having the Lindblad jump operator terms. And the other limit would be the static limit, like with magnetic field, where you have some distribution, and every experiment sort of samples one value, but the magnetic field is constant, you know, doing this one experiment which is being done. And you can generalize these models by, in addition to writing down the master equation, for example, just for the magnetic field, writing down a certain distribution, you know, which then simply says there's an underlying ensemble, and there's a distribution of the magnetic field, and we want to learn this distribution in parallel to learning the Hamiltonian. So over here we learn the jump operators, but in the other case we sort of learn what the static distribution is. And so this can be included in that if you want. In that case for the experiment here, this was not necessary. Yeah.
Okay, well, why don't we thank Peter?